series for the Llama Reading Group. Today, I'm super glad to have Dominika here with us. Actually, she's been helping me quite a bit with Llama behind the scenes. So a lot of the credit about the website and the new series goes to her as well. She's been super useful to growing Llama and opening it up to the public. Anyway, she's a second-year PhD student under Soteris Demetriou, and her work is in between security and NLP, where she's currently studying privacy preserving masking, which attempts to mask linguistic cues that may give away whether some kind of speaker or user or patient is suffering from some kind of disease. I'm sure she can expand a bit on that as well. She's also working on a really cool startup idea, which helps language acquisition. And again, I'm sure if you're interested in learning about the applications of this, Dominika will be more than happy to have a talk with you about it. And also she's presenting at Women in Computing on Friday, I believe it is, where she's going to be doing a talk/tutorial on signal processing. Dominika, I'm not sure if this is open to everyone to join or if it's just women, but if it is, maybe, especially for the women here, you might be able to give a bit more information about it.
Yeah, so thanks Nihir for the introduction. And yeah, so it's open to everyone. It's not just for women. It's to showcase just what women do in computing. So everybody is free to join.
How do we join?
So it's probably going to be somewhere on the Department of Computing website. It was in the newsletter that the DocSoc is sending, I think.
Okay, cool. I'll find it out and I'll drop a link here during your talk. Anyway, yeah, please feel free to share your screen and yeah, we can get started.
Slides. Okay, back to the right slide. Okay, so hello everyone, and today I will present to you the paper Transformer is All You Need. So this was published by Facebook Research. So this is actually quite new, from I think a month ago, that they published on Archive. But first, as Nihir already said, so I'm a second-year PhD student at Imperial College London. I study NLP and speech applied to security and IoT devices. So my interests are robust privacy-preserving speech recognition and processing, but also language learning. And my research right now focuses on detecting dementia and depression from speech and trying to hide those features so you can actually not detect those anymore. And otherwise, I also like to sail and play instruments and paint. So to guide you through what I'll be presenting you today. So first, I will introduce you to the idea of artificial general intelligence, which is kind of the driving idea behind this paper. Then I'll explain a bit more what is Unity and how they implemented it and show some of the experiments they had. And then finally end up with a discussion on the actual contribution of the paper and some of the limitations. So what is general purpose AI? So the general idea is that artificial general intelligence would be able to replicate the same task that human can do. So this is a very controversial idea just because not everyone agrees on the same components of that. So, but there are some commonly accepted characteristics. So overall, it would be able to reason and make judgments, to have a knowledge representation that can tackle many domains, able to plan, to learn, and to communicate as well, preferably in natural language to humans. And then it should be able to integrate all those skills to perform many different tasks. And if you also want to introduce it to robotics, then you should be able to sense and act in an environment. So, current state-of-the-art models in artificial intelligence can achieve really great performances in many tasks. So, for example, you would have text generation with GPT-3, BERT, which was really important for natural language understanding. Then you can also apply BERT architecture to object recognition and speech recognition as well. But all of those models, they would require you to train a new model for that specific task that you're trying to do, although they are quite general and can be adapted to many domain and tasks. So, as you might probably have noticed, many of those models are based on transformer architecture, which is kind of the state-of-the-art architecture in machine learning right now. So it is just natural that the further research is trying to apply multimodalities and multitasking to those transformer architectures. So you would have transformers that would try to be able to take images and text, which has two modalities among many others. You could include audio, you could include videos. If you want to include it to robotics, you could also have any type of sensors that you want to have. But in here, I think the most common are images and text. So you would have visual BERT and VidBERT and CLIP that here presented not that long ago, and DALI as well. Here we'll be combining two different modalities. But you can also have transformers that have been adapted to handle many tasks. So you would have T5 that can handle many tasks on text, then VilBERT Multitask, which is VilBERT adapted to also have many other tasks, and similarly for Multitask domain, the deep neural network. So what is Unity? Well, Unity is doing the same thing as the previous work, but expand on it. So it's also a transformer architecture. It has an encoder and decoder model. It also just have two modalities in here, so it'll be images and text, but it expanded to 7 tasks on 8 different datasets. And this is a model that is trained end-to-end, and it achieves comparable performances to task-specific models. Here, what it would look like for Unity, so you would have many different inputs. So you would have, for example, an image. You might have a question related to that image, a hypothesis, premise, or just text that is not related to the image. And then you would have here 7 tasks where maybe you just want to do object detection on that image and discard all the other information, or you want to do just sentiment analysis and discard all the other information apart from your paragraph, or you want to do joint tasks. So you would have the image and the text, and you want to maybe answer questions or check whether that text represents the image. And then you would have then multiple tasks that could take all those inputs and outputs, all of them at once. So the tasks presented here in this paper are single modality tasks. So for vision, you would have object detection. And for text, you would have then question answering, textual entailment, question. They have 2 datasets for question answering, and then sentiment analysis, and also joint tasks, so visual entailment. So we would be combining images and text and try to combine where one text corresponds to the image, or you have an image and you try to answer the question, and this would be visual question answering. Here's an example of what it looks like. So you would have, here object detection, 2 datasets. So you have the COCO dataset and the VG dataset, but you also would have visual question answering. So you would have images and text, or visual entailment. So again, it would be image and text, but here you're trying to see if it corresponds to it, or you would just have text or just images. Now let's go into how to actually implement this and what's the architecture. So this is the proposed architecture for Unity. So you would have, for each modality, you would have an encoder, and these encoders would output the encoded representations that they would get concatenated, so just appended to each other, and then fed through to a decoder that would then use the concatenation of the representation for each modality and perform cross-attention on the encoded, on the task-specific embedding, and then output it to each task-specific head, so it can perform each task. So how it looks like in terms of actual implementation. So for image modality, they first extract the feature with a CNN. So in this case, they use a pre-trained ResNet 50 encapsulated. And then to extract the representations, they also append to it a task-specific embedding to force the model to associate the type of features that it wants to train on with a given task. And then it feed it through a visual transformer encoder. So similarly for text, you also need to encode them with a text-related encoder. In this case, they just use BERT and not even the bigger model, just the base model to encode the task modality.
Would you like us to interrupt you for questions, or should we wait?
Sure. Sure. If you have questions, sure.
Yeah, on the image encoder, and I just asked because I might actually use this in some of the work I'm doing. So what they're doing is they're just feeding an image through a ResNet 50, and you get like just one vector, and then they're concatenating the task-specific index with this vector, and then feeding it into the transformer.
Yeah. Yeah.
Okay.
Exactly.
So essentially, it is just one vector which is going into the transformer.
Yeah. Yeah.
Okay, interesting. Like a whole transformer for that seems very overkill if you can just concatenate the text input to an image feature. Okay, cool. I guess what I'm saying is if you go back a slide, another one. to where you had the whole architecture. Like this image input, which is coming into the CovNet backbone. So that will come in as one, like just a d-dimensional image feature. And what will come out of all these transformer layers is also one d-dimensional image feature again. So it just seems like you're doing additional processing just to have this concatenation going on. So they're not feeding in like any object features or anything in the image input. It's just the one feature vector, right?
Object features, what do you mean by that?
So, you know, one of the outputs of the decoder is that they try to predict the objects which were in the image. They're not feeding any of those objects information in as input. It's just the one image feature after feeding it through ResNet.
I'm not sure what you mean.
Okay, it's just, okay, so you just have an image, you feed it through ResNet, and then you feed it through the transformer stack.
Yes.
Okay, cool.
But you could be, I haven't read the paper, but you could be getting not just one vector as the image feature, but feature maps, for example. Yeah,
that's what I'm thinking. That would make a lot more sense if they were to feed in, object features instead of just one image. It reminds me of what Marek was saying about my work the other day, where what are you running attention over when you just feed in one vector into a transformer? It's just gonna, the only thing it can attend to is itself.
But it could be object features if there's detection, or it could be actual just feature maps, which is not really objects, but some.
I think actually it might be feature maps that they're including. Yeah. Then
Okay, if it's feature maps, that makes more sense.
Mm-hmm. Oh no. Okay. Oh yeah. Right, and then you would take the concatenation and you would pass it through the decoder, and this one is always the same, regardless of how many modalities you have. And they ended up having it shared, but they also experiment later how it would be if each task would have its own decoder. And then you would have, for each of your tasks, you would have specific heads. So you might have a data set that have multiple tasks, so you would need a new head for each task, basically a new classifier. And again, if you have some data set that maybe have a different number of output classes, you also need a new head. Okay, and here just go back to the overall picture so you can put them together. So you would have the encoders, concatenation, decoder, and then task-specific heads. So in terms of some training details, so because they need to train the model with all those tasks, they decided then to, at each step, to pick randomly one task. And also they realized that for object detection, they actually have this imbalance of number of iteration that they required. So for example, a simpler task would be visual question answering. They would need more, it needed less iterations. So they had to mitigate this issue by already pre-training a model on object detection and initializing then Unity with the pre-trained weights. So then it can fine-tune together with the visual question answering. Okay, so now in terms of experiments, so they explored how does the single task perform versus the shared architecture, and also whether the separate decoder would do anything or would be detrimental. So in the first experiment, they just focused on object detection and visual question answering. So there's one single class and one joint task. And then in the second experiment, they expanded to also more NLU tasks and compare it to all the other models that were trained on those data sets. Oh, yeah, it's a bit blurry. Yes, so this is the results for the first experiment. So the COCO dataset and VG dataset are for object detection, and the VQA V2 is for visual question answering. So the first row here is for the model that is trained on the single task, so it's not trained jointly. And then here it's the framework trained together with all the other tasks, both for separate decoder, so each task would have its own decoder or shared decoder, or a decoder initialized with pre-trained weight for object detection. So one thing we can notice is that the separate, so here actually the shared decoder and initialized with COCO had the best performance for the object detection in both cases here, and it had it also improved over the single task for the visual question answering. Although here, this joint task actually somehow benefited for a separate decoder. Also, we can see that the single task for object detection improved here for VG on the shared, but it actually was detrimental for the COCO task. So in the second experiment, when they added more modalities, so in this case now they're using the 7 tasks and the 8 data sets, the results are a bit different. So again, the first row, the single task training, so this would be their baseline, and then here would be when passing it through the framework and training it jointly with all the other tasks and data sets. And then the last here block is to compare it to other models that were using those data sets and that reported their accuracies and performance on those. So here we can notice that actually only 2 tasks, which are the joint task, benefited from this framework. So here as a single task, they would have, for example, 66 accuracy, and then when trained with the framework and shared, they slightly improve here for VQA V2. And for, I think it was visual attainment, it also improved from 70 to 73. So those 2 tasks actually improved. But looking at the other ones that are unimodal tasks, they actually suffered a bit from this shared training. So this is the case for COCO and VG, and also all the other ones that you can see that it goes from 91 to 87, 84 to 80, 91 to 90, 91 to 89. So they actually suffer from this. Now, when we compare the framework baseline to the other state-of-the-art models that were using those tasks, it performs similarly, although here 40 and 43, similar here, a bit worse here for visual BERT and visual attainment, even with the shared tasks. And then, here the baseline is similar to BERT with a classifier, here a bit better even for the textual attainment, and similar for the question answering, and sentiment analysis is also similar. Another thing to note is that the VG task here actually got worse as we added more modalities, because you can see that here previously it actually improved from the single task to the shared task, but as we added more, it actually decreased in accuracy. So that's something interesting, I guess. As it scales, these models can be more detrimental to single tasks. So yes, as we could see that only 2 tasks benefited from the shared representation. So the joint task, they use both modalities, which in a sense, it makes sense because it benefits from different representations. And while the other task probably should just discard image representation if it's text and text representation if image. And it was able to still have comparable performances to task-specific models, even when the single task suffered a slight accuracy decrease. So in terms of limitation, I guess it's not really limitation per se, but just some unexplored areas. So as we saw that as we added more modalities, the single modalities suffered, the single tasks suffered. So how it would scale as you would add more, that would be something that should be experimented on. Another thing is that you do need to train a new head for each new task. So you might have a big model that they can do many tasks, but if you wanted to do a new task that is not treated by this model, you would have to do that as well and fine-tune your model on that. Also, it does not really mention how it would perform if you were to use this model that was trained on all those tasks, and then you wanted to use that to fine-tune it on a more specific task. I think it would be really interesting to explore. So so in conclusion, T is a single transformer model that handles text and images, and it can handle both single and joint tasks across many domains. And the performance on joint task actually improves thanks to the shared representations, and it still reaches comparable performance on single task as more task-specific models. And because it can handle many tasks at once, and you don't need to train a new model for each task because it has shared representation, it actually reduces your parameter size. If you were to compare it to 8 different models for all your 8 different tasks or 7 tasks. But I think that more experiments would be interesting to overall test how would this model scale and how it would generalize well. So that concludes my talk, and thank you very much. And if you have any questions.
Yeah, thank you very much for that, Dominika. Great talk. I definitely picked up a couple of new things there. Does anybody have any questions for Dominika to kick off the conversation?
So maybe I can start at, maybe you went a bit faster in the beginning when you were comparing to this other multimodal representation learning approaches such as, I think you mentioned Bilbert, and then there are things like Alex Merge, where there's also multiple pre-training tasks. So I didn't quite get what the main difference would be with this one.
So I guess the difference here is that, yes, they're using the same multimodal. So here they're able to handle both images and text. But yeah.
Can you go to the architecture again? Maybe we can have a quick, the full architecture again.
So yeah. So I'm not quite sure how is the architecture of Wilbur different to this one. It might be that this one is more efficient, but I need to check what they need to do.
And I guess there's some things that are different, such as, I guess, this cross attention that you have here. I don't know, in some of these other works, they were doing things like masking objects to predict word, or masking words to predict objects, and this is how they were getting the multimodal representation, which I'm not sure is exactly what is happening here.
The task specific heads, like, how does it know which one to use? So I see that there's like a task index which is coming into the decoder. Is the task specific output head that it chooses based off that task specific query embedding, or do you think there's more just like an if statement in the code which says if task index equals 1, then do object detection or run the object detection head?
Yeah, I think that's the case, because they leave all the tasks to output what they want to output, but then they discard what is not relevant to the task that they decided on. So I think it's more of, yeah, they know which task to go for.
So, you know, yeah, I guess the line between general purpose and not general purpose is a bit blurred here, because, you know, I guess in one sense it's general purpose because it can support multiple tasks, but in the other sense it's like you have to have support for this specific task to be able to actually use this. Yeah, so exactly. Yeah, I guess this bridges on well to a question that I had when you were talking about AGI, and coming into this presentation, I was just thinking, like, is the solution to AGI just a lot more data? Because if you take a look at GPT, for example, you know, they just threw a huge amount of data at it, and obviously you get a really good language model. But here, you know, the encoders and the decoders, they're receiving a lot more language data than just one task-specific transformer. Yet we're not seeing any comparable, or we're not seeing any improved or strong improvements in the actual metrics. So does the paper talk about why the results are comparable and they're not performing, but they're not outperforming, you know, those existing state-of-the-art task-specific models?
I think the issue here is that the model, you know, as you increase in number of modalities and just modules and encoders, you actually increase your feature space. So I don't think there's a real, apart from the presentation, I don't think there's a real mechanism here to differentiate from the features. So I can see that from the single task, it becomes noise rather than actually helpful. While for the joint one, it was helping because they were using both features. So I think that's the issue, is that there's no real, apart from the this task embedding that they concatenate to the modality embedding, I don't think there was anything more there.
Yeah, I guess it just plays my intuition a little bit, because I thought, you know, for each task, the decoder is still going to be receiving like 8 times the information, because you have 8 times the data sets on average. Like, you know, if you had a task which was just 1,000 batches, for example, then your decoder goes through 1,000 batches and that's it, you get a certain performance. Whereas, you know, despite the decoder not decoding, for example, VQA when it's been given, or not doing a VQA objective when it's been given an object detection objective, it still has to process that information through the decoder. So, like, you know, very, very loosely speaking, this decoder is receiving, and the encoder as well, is receiving like 8 times the amount of information than a task-specific model would do. So yeah, I guess that's a point which has me a little confused. Like, why isn't the language model better than the task-specific models?
I think it's just because those features become detrimental to the tasks. So more features not always good. Like sometimes it's just it worsens your performance. And I think that's something that often happens in multitasking, is that sometimes the shared representation are not helpful.
Yeah, I guess it's just because, we've seen other transformer-based architectures, such as, GPT is just the first one that comes into my head, which obviously was just trained on, generation, so next word prediction or something. So even though I guess it's not task specific in that, or it's only one task in that sense, still because you're receiving a lot more data, that the model is a lot more powerful. Did they talk about hyperparameters they use in this setup?
Yes, they do.
The size of the transformers, so like how many layers were there and how big were the hidden dimensions inside of it?
So I see the dimensions for the decoder. Yeah, of course, because they're using, for the text encoder, they're using BERT, so they have, I think, 12. Yeah, so they just mentioned the number of layers for the decoders because they tried to experiment with this to see how it would affect their architecture. Yeah, so I think they got 8 layers for the decoder, not 6.
Okay, so I guess that is relatively small compared to, or very small compared to what GPT would use. So yeah, maybe, well, obviously direct the number of encoder layers and decoder layers. The more you have, the stronger your model is going to be, it seems. So I wonder what would have happened if they scaled this up for it to be bigger than just 6 layers. It could have been quite interesting. What other questions do people have for Dominika? None? Cool. Awesome. Yeah, in which case, Dominika, do you have any final words to add?
No, I think that's all for me.
Oh, cool. Yeah, great presentation. Probably about the length it would take to explain this architecture. So yeah, thank you very much for that. Yeah, so next week we have someone from MIT. His name is Kieran. He's going to come in and give a talk about some really interesting work that he did on scraping WhatsApp data and using that to detect how memes can basically influence people's perception of the news. So yeah, really excited for him to come and give a talk about this. And from the latest I know, he's going to be joining the Imperial team as well. So if you guys are at Imperial, could be a chance to say hello to a new team member.
That's not decided yet. So.
Sorry?
That's not decided yet.
Oh, okay. So that's not decided yet, but potentially. Okay, cool. So I'll send out an email with a bit more information when everything gets confirmed and finalized. But apart from that, it's great to see you all, and hope to see you guys next week.
Thanks, Dominika.
Thank you.
Bye.
Bye.
Thank you.